electrochemistry and oxidation, reduction reactions. Okay. All right. So where does electricity come from? Well, the most common place that we get electricity from, yes, it's the flow of electrons, but where does it actually come from? Where do we get our electricity from? Right. Okay. Does anyone have a correct answer? Anyone have any ideas as to where we get electricity from? From the magic hole in the wall, right? Yeah, what? Sorry, the they use coal, and then they turn the turbine. And it turns a turbine, and how does that turbine work? Okay, here I really do find it fascinating. This is a topic that I teach often, like in my Earth Systems class. Essentially, no one knows how electricity is made, which is we use it every second that you're awake. Okay. It's frustrating that we don't know the simplest thing about the most common resource that we use. Yeah? Has anyone seen an alternator out of a car? No? Yes. It looks like this. Wait, what? Yes, thank you, Repeat. Magnets. Well, neither does anyone else. We don't know why it produces electricity, but we do know that it produces electricity. It makes the electrons move. That's all we need to know. In order to understand why it makes electricity, we would need to understand why magnetism is a thing, which we do not. We do not understand why magnetism is a thing. We don't really understand. We understand how magnetism works, but we don't understand what the driving force behind it is. Okay. This is an alternator. You spin this thing, there's magnets inside, and then there's a coil of wire. If you spin magnets inside of a coil of wire, you create electricity. That is what a turbine does. Okay? Please know that. Just know that. Like, to be an adult, you know? Because I guarantee you, if I go out on the street and I ask 100 random adults, maybe 10 of them would know this. And that, my friends, is disappointing. So, people don't know where a single country is on a map. Yeah. Do you?
Did you see the one where people have to like?
There's a video, I think it's from Jimmy Kimmel. It's called Name a Country. And they show a world map of unlabeled countries. And they say, name a country.
I would be able to say that.
And a large number of adult human beings could not point out a country. Australia would be very easy. I would argue that most countries would be pretty dang easy.
I would argue that America should be.
The United States of America is a very large, very, like, come on. Anyway, so this is how alternators work. Okay, you spin magnets inside of a coil of wire, right?
There's some people that think the smallest large landmass and smallest million.
The smallest large landmass. They'd probably point to Greenland. Okay. So there's turbines. Today we're going to talk about the other source of energy that we use, and you are all, well, not all of you, but most of you are currently using this source of energy right now, and that is batteries. Okay? You use batteries every day in your phones, in your laptops, in your freaking Game Boy original. Those pop in those 4 AA's and switch it up. Has anyone held a Game Boy original? The gray brick?
No. Yeah. I have gray brick.
So the gray brick, that was the original Game Boy. That's what my twin brother and I had. Oh yeah, Pokemon Blue, Pokemon Red.
I played Mario on mine. I played Pokemon.
Okay, batteries are a chemical reaction that moves electrons. That chemical reaction can be defined as an oxidation reduction. Most chemical reactions that we discuss in this class, unbeknownst to you, have been oxidation reduction, also called redox. Okay? Redox. Oh. So a redox reaction, so remember when we talked about acids and bases, right? An acid and a base, acids consist of free hydrogen ions, right? Free positively charged ions. Redox reactions, so acids and bases were all about the movement of protons, positively charged ions, right? Redox reactions are all about the movement of negatively charged ions, or just electrons, okay? And we have talked a lot about electrons, but we haven't used the terminology redox reaction, okay? Molecules or atoms, okay. We talk a lot about electrons, but we haven't used this term of redox. Okay? Redox reactions are oftentimes discussed as a part of like batteries and so forth. Okay. One of the most common redox reactions is a zinc ion and copper. Okay, zinc and copper. Sorry, okay. So zinc and copper, and what happens is that the zinc and the copper exchange some electrons, right? Exchange some electrons, which is pretty common, right? Sorry. Okay. When they exchange the electrons, it's a lot like ionic bonding. Okay. We know what ionic bonding is, right? What is an ionic bond? Anybody? Huh?
It's when one atom like gives up one electron and one atom gives an electron.
Yes. When one atom receives and one atom gives electrons, right? So in the case of a copper zinc redox reaction, we're going to see that the zinc is actually going to what? Did you move everything? Thanks, bro.
Oh, I did find an egg.
You found an egg.
I found an egg in your car.
Awesome.
I don't know what to do with it.
Go smash it somewhere.
Smash on purpose.
You think I can get an omelet?
I'll give you a dollar. I want
Incubate it.
Sean, you remember those confetti eggs the last time we had a field day?
Yes, I do. Okay, so copper and zinc, what happens is the copper receives 2 electrons. Or takes 2 electrons. And the zinc gives up 2 electrons. All right. So what that looks like is we have a zinc atom. Sorry. So zinc. The zinc atom reacts with a copper 2+ ion. Huh? Yeah. And that becomes, and I'm going to come down here because I don't know if I'm going to have room. That becomes a zinc +2 ion. Or 2+. And a copper atom. So what is happening here is one of the elements is being oxidized and one of them is being reduced. Okay? So in oxidation reduction reactions, one gets oxidized, one gets reduced. Okay? Oxidized means that oxidized element. The oxidized element gives up its electrons. Electrons. Okay? And the reduced receives electrons. Okay? So in this case, which of these 2 elements is being oxidized? The what?
Wait, the copper. Yeah, copper's giving up its electrons and reducing the
Is the copper giving up its electrons?
Oh, yeah. It's actually giving
the electrons are moving from the zinc to the copper, right? Because the zinc goes from a neutral charge to a 2+ charge, meaning that it loses 2 negative charges. Okay? It loses 2 negative charges, they go to the copper. The copper goes from a +2 ion, it takes 2 negatives on, thus making it neutral. Do we see how that works? So in this case, the oxidized element is the zinc, and the reduced element is the copper. Okay? And just for context, this is what this looks like in real life. Okay. By alternators. Okay. So zinc plus copper goes to zinc plus copper, right? But there's an exchange of electrons. And the way that we write this down is in what we call a half reaction. What is it? Oh, the egg? Yeah, you probably could. Half reactions. So a half reaction is exactly what it sounds like. You can also abbreviate it as half Rx. Okay. Does anyone know what Rx usually, like where do you usually find an Rx? Prescriptions, pharmacies. The Rx actually comes from reaction chemistry. And that pharmacies use chemistry to make medications, right? Okay.
Why can't we go back to like prescribing cocaine?
Prescribing cocaine. Jack, I think that you know the answer to that. Okay, so the half reaction for this is we're looking at just one thing, okay? Just one thing in a half reaction. So for instance, let's look first at just the zinc, okay? Let's look first at just the zinc. The half reaction for zinc is going to look like this. You go from Zn, arrow, to Zn, 2+, plus 2 electron. Right? So this is the half reaction. You're going from a regular zinc atom to a zinc ion and 2 electrons. For the copper, which is the other half of this reaction, it's going to be like this, Cu2+, plus 2 electrons equals Cu. Okay, so this is half reaction 1. This is half reaction 2. Do you see how that works? More or less. Maybe?
Yeah, the thing does the thing.
The thing does the thing.
The thing does the thing that causes the thing.
All right, let's look at another example. Okay, let's look at another example. Let's look at magnesium right? Magnesium and oxygen. And in this case, it's O2 and 2 magnesium. And these make 2 magnesium oxides. 2 MgO. Okay? So we have 2 magnesium atoms reacting with 1 oxygen molecule, which has 2 atoms, to make 2 magnesium oxide atoms or molecules, right? So, based on what we understand about the periodic table, which of these two is more likely to take the electrons or receive the electrons? Remember, we're looking at Mg and O. Mg and O. Oxygen is what? What? More likely to take the electrons, right? Because it is very electronegative. Do you remember why we know this? Why is oxygen electronegative? Because its valence shell does not have enough electrons, and it's quite close to having enough electrons, right? It just needs 2 more to be full, right? And magnesium, how many electrons is magnesium more likely to give up? Probably 2, right? So oxygen wants to give up 2, magnesium wants to give up 2. That's a nice pairing, right? It's a nice pairing. So magnesium giving up 2, oxygen taking 2. So in this case, which of these two is going to oxidize, and which of these two is going to reduce? So what is oxidizing? Wait, what? Oxidizing is taking electrons, or which one of these is going to be oxidized? The magnesium is going to be oxidized. It will undergo oxygenation. Oxidation, there we go. It will undergo oxidation. Do you see the name oxygen? This is where this comes from. Oxygen oxidizes magnesium. So magnesium will undergo oxidation. Does that make sense? Magnesium will be oxidized, and the oxygen, excuse me, will be reduced. Fluorination. Yeah, fluorine is not a very common element. Oxygen is much more common. So yes, I 100% agree. It would make more sense if it was called fluorination. However, fluorine is very rare. Hello. No, I don't believe so. Yeah, Carlos, yeah, what about him? He is not. Oh, wait. Ben Daniels is supposed to be in my class, but he's not here today. Okay. Yeah, hopefully. Thanks. What's up?
Do you like Fire Red?
Do you want what?
The Pokemon game? Pokemon Fire
Yeah,
Red?
dude. Okay, sure do. Okay, so oxidized, magnesium is oxidized. Oxygen is reduced. Okay? Magnesium is oxidized, oxygen is reduced. Now, we need to write, now we need to figure out what their oxidation state is going to be. All right, their oxidation state is essentially just what kind of charge they're going to take on. All right, so based on what we know from the periodic table, we know that oxygen wants to have a -2 charge, right? It wants 2 more electrons. So the oxygen is going to be a 2-, and the magnesium is going to be a 2+. Does that make sense? 2- and 2+. Okay? Now, if we were to write the half reaction here, it would look something like this. Let's look at just the magnesium first. The magnesium is going to go from Mg, Gesundheit, going to go from Mg to Mg2+, and 2 electrons. Repeat.
Why don't we put like the closer and the addition and subtraction sign behind the number instead of or
2+ instead of +2?
Yeah.
I do not know, because chemistry is weird. And then the oxygen is going to go from an O to, oh, sorry. Screwed it up. It's going to go from O, and then we add in 2 electrons, right? Plus 2 electrons, and those 2 electrons come from the magnesium to become O2-. Okay, don't put the 2 down here, because that would suggest that it's 2 oxygens, right? O2-, that's the half reaction. Okay, we need to do one more example real fast. We're going to do aluminum. Whoa. There we go. 2 aluminum plus 3I2, 3 iodine, makes 2 Ali3, 2 Al. Okay. So, which of these 2 elements, iodine or aluminum, is more electronegative? What do you mean it's positive? Oh no, +3. It's not a +3 ion. So, excuse me. Iodine is the more electronegative. We can look at the periodic table. And we can see that iodine is just one electron away from being a noble gas, right? Just one electron away from being a noble gas. So we know that this is going to oxidize aluminum. So aluminum is going to undergo oxidation. And the iodine is going to undergo reduction. Okay? What are the oxidation states going to be? What are the charges going to be? Now we need to look at the number of atoms. We need to look at the number of atoms. How many electrons does each iodine want? One, right? And how many iodines are there to each aluminum? We have 2 aluminums and how many iodines? We have 6.
Oh, yeah.
6 iodine atoms, 2 aluminum atoms. So if each iodine is going to be -1, 1 minus, if each iodine is going to be a 1 minus, and we have 6 of those, we only have 2 aluminums. How is that aluminum going to compensate for the 6? How are the 2 aluminums going to compensate for the 6 negatively charged iodines? So the aluminum is going to have what charge? A single aluminum will have what charge? It'll be positive, but what will the quantity of its positive charge be? We have 6, 1 minus. We have 6 of these. So we have a -6. We only have 2 of these. What is the charge going to have to be in order to compensate for that? Come on, guys, this is not hard. 6 split up between 2 atoms.
3.
3. Holy crap, guys.
Wow, that was so
Okay, do we see how that works?
No.
No. Okay. We have 6 of these, right? 6 of these. We have 2 of these.
So therefore, I was just going
So we have a -6 charge between the iodines, and we need to have a +6 charge between the aluminums, but we only have 2 of them. Okay? So the half reactions are going to look like this. Al. But we have 2 of them. Two Al. Oh, sorry, not plus. Shoot. Go to goes to 2 Al3 plus. Plus how many electrons? How many electrons are going to be released from 2 3 plus aluminums? 6. 6 E minus. Okay? Calculus. This isn't even algebra. This is like basic arithmetic. I plus, well, we have 6 iodines, 6 iodine plus 6 electrons makes 6I 1 minus. Do we see how this works?
No, but I'm gonna say that.
Okay, there is an assignment called electrochemistry. It is due on Friday. It is this. You have to identify which element will undergo oxidation, which element will undergo reduction, what their oxidation states will be, and you need to write out the half equations, half reactions, okay? Like and subscribe or whatever.